it rains, it's gonna rain. And you know it's still the end of the think about it differently. You will not see it. Yeah, oh my God, yes. Yeah. I was about it early, and it was only half of the class because nobody competed. I'm saying it's going to be a small class. It's 8. It was really great. Very cool. Very cool.
Can I ask you a question? So does the, I'm really not sure about the VC dimension, but does the general idea come from the time that they're trying to show the capacity, I mean, the capacity of neural networks?
Yeah.
Because it's
pretty old.
So they were trying to show, I mean, how neural network how many layers or how many nodes does a neural network need?
Yeah. But in general, it's like just basically trying to prove certain things, like so you can prove, for example, that a neural network is capable to approximate any function with a certain accuracy or with a small error. You can solve convex problems. Yeah. You have 2 layers and so on. Like there's many application areas.
This slide
It's more of like this comes from it's not even practical. Yeah, I was looking at the page of the guy, but they are Russian, so.
Botnik, yeah, they're Russian.
Yeah, so really deep mathematical understanding.
For the lecture 3 that you uploaded on Blackboard, is it a little different than the one you're talking about today?
Oh, lecture 2 was last week. Like it's kind of like I can split them.
Because I don't see the pack example that you just went.
Yeah, no, that's in lecture 2.
Oh, that's in lecture 2.
Yeah.
Oh, okay.
Yeah. It's complicated. I could split them, but like that would confuse me now.
Yeah.
That's very cool. It's very cool. Except the rest of stuff.
Yeah, I would just have to like change a couple of slides.
Yeah.
I'm lazy.
Oh my God, I forgot. It's been 30 years. I have to just start going back to physics. Oh my God. You forget. So then you can show me. It's supposed to be. Actually, I never asked.
Also, I should mention that there is a wrong homework assignment in there. Just disregard that.
Okay.
So these are the control theory and the matrix.
Yeah.
Alright.
I'll fix that real quick.
But then you start going into these. Yeah, then you read it's mostly what it's so I went only through the first part, and I literally had to write lines and lines to remember. Yeah, that's what. There's a lot of it's all math. It's all math. Because there's the idea is this.
Yeah.
So basically you have to model, first model systems as if you were doing, you do a MATLAB model. And then everything else is MATLAB is going to do that. MATLAB.
So Wednesday
But we're going to do something later, so it's perfectly. No, for robotics, there's some Python applications.
Okay, let's continue. And so for next, for Wednesday, I'm thinking that I will talk about like how to run machine learning experiments and leashing. We'll talk about the scikit-learn tutorial. So we're going to have like an intro on scikit-learn and what it can do. So that it is a very powerful toolbox that basically has all the basic classifiers and even advanced models in there for classification, regression, visualization, etc. And what I want to focus on Wednesday on, like in the first hour, is basically like how do you set up a machine learning experiment, and how do you train your classifier, and like the most important part there is that we don't just want to train one classifier to like see how well it does on a like data set, but we need to like validate the classifiers, and we also need to evaluate. So validation, in a sense, helps you find the optimal hyperparameters, and evaluation then allows you to actually assess the classifier's ability to the classifier's ability to generalize over all the data sets, or all the data points, over data points that you haven't seen yet, and stuff like that. Okay, so regression in that case now is a little bit of a different problem, and basically what we try to find here is a function approximation. So given a data set, or like data points like these blue ones, we kind of like try to find a line that expresses them accurately, but not too accurately and not too like limited in a sense. And so X is basically just our enumeration of data points, and Y's are the target values again. And so as you can see, while this line here kind of fits the data set quite well, like I would say it expresses it fairly accurately, it only like touches maybe 3 data points out of this data set, okay? It doesn't have to go through every single data point here. If it would be some weird curve like this, which doesn't really approximate what's going on here, right? So we have these observations Y, but they're not necessarily characterized by this zigzag function, but more by this like low-dimensional function, which is this regression line in this case. So instead of classification problems where we have categorical targets like zeros and ones, we now have targets that are any number in R, and we need to learn not a class but a numeric function, which is f of x, but we don't know this function obviously, and all we have again is target inputs, or like inputs and targets, right? We would like to find a function that basically expresses this as close as possible. Why are there animations on my slides? This is so annoying. Sorry for that. This is a bit weird. Yeah, 1 second. I think when I saved it, like it started to just create this weird animations. Okay. So we try to like find the function that approximates f of x, and like in our classification problems we don't know this function, right? And so what often is the case is that to this function actually there is some error added, or some noise. So we don't actually like have access to this to the entire function, and we have like there are hidden variables that influence this, and these hidden variables could be noise, they could be other parameters that we're not monitoring, or they just are not accessible to us. There could be, for example, I don't know, like the walking speed of human beings is dependent on the length of their legs, but also some other variables that we don't have access to, like their mood or their, like if they are injured or whatever, but there's a trend. So we want to find a relationship between the walking speed and the length of legs, but there is some variability to all of these. And because we only have one-dimensional input, which is the length of the legs, we don't have, we cannot model this parameter, but we can still try to approximate this function, okay? So there are a number of hidden variables that we don't know about, but we try to still approximate this, and we seek to approximate this through our model, and this could be a line, it could be like a polynomial, and so on. Okay, so we just want to try to like use a function that like goes with the input data points, and we evaluate how well we're doing by computing this function here. And basically, what this does is nothing but it calculates the average error or the average distance of the actual target y t is in this case just a number in the data set, minus the predicted y that we have, okay? And we take the square root, so this is some Euclidean distance, and so what we try to find are predictions that are close to these y's, okay? And this could be 0 all the time if we fit it perfectly. It could be some small number, but basically we evaluate our model by this empirical error, okay? And we try to optimize this. And we optimize this again basically on a hypothesis space. So for example, so we again want to minimize this error, and in case we assume that g of x is linear, our hypothesis space can be defined by a set of parameters, which are these w's, and we can have d many w's, and we just like make a linear combination, for example, and that would be one. If we wanted to make this a polynomial, we could do like wd x1 to the power of d, for example, right? And like to the power of 1 and to the power of 2 and so on. So we can make this a very complex polynomial in this case. But we can also just leave it like that and say, let's come up with a linear function. In the simplest case, d equals 1, so that would basically just be a line, okay? And even this w0 could be 0, and in this case, just like a biased term. And so for this simplest case, we can actually compute this fairly easily, and we can optimize this right away. So we replace our g function here by just this term, and because this is what we want to do, so we want to optimize the distance between our predicted y values and the actual y values. And we can optimize this simply by basically doing the following. So the minimum point can be estimated by taking the partial derivatives of e for the parameters w1 and w0, and then set them to 0, right? So because so we derive a function towards one and the other parameter and just set it to 0, because that's where there is no steepness in the gradient, so that means it has to be a minimum. And if we do this for w1, we come up with this function, which is dependent on the inputs, the targets, and their mean values. And for w0, we just have like this bias term, which is dependent only on the the mean values. Okay? And this is our solution. This is basically how you find a regression line. This is like for all linear regression lines, this is your formula to find that line that we had previously.
So we don't have any local minimums, right?
No. Yeah. Not in this case. Yeah. So it's just there's one optimal solution for this problem. There's also kind of like a nice thing for these regression because you see everything, right? Like you have all the data, but obviously, like if you wanted to use this to predict future data points, you would have errors sometimes. And yeah, you can make this a higher polynomial. You can make this squared, and your the set of functions that you have to optimize is just like increases through that. Okay. And as we discussed earlier in the lecture, while our error becomes much smaller if we increase the power of our regression, it doesn't necessarily mean that we're having a better approximation of the underlying function. We just might to start modeling these weird noise terms or noise variables. And remember the Occam's razor that we discussed last time. So as an example here, you have these data points which are marked as x's, and you have a straight line, which is this one here, which fits quite well to the data set. A quadratic function that basically has this kind of curve in there doesn't fit as well again, but then the order 6 polynomial fits the data points perfectly, however likely overfits the data and doesn't really express what is happening. So I think in this case you could either stick to first order or a second order polynomial to fit your data. And the cool thing about regression in many cases is that it makes a lot of sense to just try it out and see how it is visualized. Like you can see a lot from your data when you visualize it for yourself, and so you can see nice functions there. Okay. Questions to that? All right. And you saw that we're gonna read this paper. I think I said that it's due tomorrow. It's not that hard of a paper. It's quite instructive, and it gives you just a couple of nice overviews of like what important things are there to know about machine learning, and we'll probably briefly walk through a few of them and just bring your notes that you made and like be able to kind of like discuss a few of those. I guess like overfitting is one in there, like validation and stuff like that. Okay? Alright. Oh yeah, and submit those notes as well, please, so that we have it on file, so to say. Alright, and now this is kind of like, this is from the third lecture that I uploaded, and this basically just gives you kind of like an additional idea of like for data handling, and this could also, it's more practical, like after all this theory stuff, let's talk a little bit about some practical applications. And basically what we have to deal with are these data representations. So we have some sort of input, we want to compute some function, and we derive some output from that. But like the entities that go in, and it could be human behavior, for example, or like just information about a human, they need to be mathematically represented, and like in the general case, this is very practical and should be clear to everybody. Like we always define data through an attribute value kind of pair, So, for example, we would have height, which is in centimeters, eyes, which is in blue, green, brown, and jobs, which could be anything, right? So, while this is numeric, that's fine. We can just use the 180 centimeters. We can normalize that as well if we want to. And eyes is kind of like a finite set. It's not too many. But then jobs, for example, will become very difficult to model that and to insert that into machine learning algorithms. So that could be too variable, and like we might even want to get rid of that. But anyways, so. And these input like attribute value pairs, they can be called like an unordered bag of features. So it's just like there are different types of attributes in there. They could be categorical, ordinal, or numeric. What we like most is numeric for machine learning. Ordinal is quite okay as well because we can translate that direct into numbers. And categorical, well, in natural language processing, you have everything is kind of like categorical. Everything is kind of like an entity, and there are actually really interesting and new machine learning algorithms that derive numerical values for words that still have like attributes like they have dimensions implicitly represented that pertain to, like, for example, gender, or for job, or relationship between countries and capitals and stuff like that. So there's some very interesting stuff going on, and we can talk about this as well at a later stage in the class. But anyways, so just so you know, there are these different types of instances, and the cool thing also is about, like, for example, with Python. If you have these different types of variables, it's quite easy to deal with those. Like you can mix them in your data sets, and you can replace those. So C, for example, isn't that great to deal with these different types of attributes. Let's talk about a little bit about like categorical attributes. So they basically fall into a mutually exclusive category. And in practice, they can be encoded, for example, into numbers, for example, and it's important that there's no natural ordering to categories. So you can basically arbitrarily assign a number to it. You don't have any advantage of, like, if you order them logically, right? And you cannot do many operations on those. You can just check if it's the same or not, because there's no greater or equal, greater or smaller relationship to those, which exists in ordinal attributes. So again, instances fall into a category. However, they have some sort of natural ordering. So for example, education level goes to postgraduate, Likert scales, disagree, neutral, agree, strongly agree, and so on. They kind of have like these ordinal scales. And you can keep those orderings constant in your data, and you can make some meaningful comparisons with values. However, don't necessarily use average variance too much. In Likert scales, you kind of can, but it's not that meaningful still. Okay, so logical operations are like more in line here. Also, like, just to be careful also that sometimes hard to differentiate between categorical and ordinal scales. So for example, single married divorced, is this a natural ordering or not? Like, very difficult to say. And like, you know, married afterwards again, or so just be sure, like, to think about it properly. And it often doesn't make sense to use the categorical ordering, or like to use an ordinal ordering, but just be careful on like what operations you're kind of conducting in them, like trying to get something from it. Okay. All right. So Then the ones that we like the most, numerical numbers or numerical attributes, which are basically integers or real numbers. Most of the time we treat everything as real numbers, like even if it's just like values like these. And we can compare them in many different ways. So we can do mean, variance, standard deviation. We can add, subtract, and divide them. This is really all cool. So you realize that like dividing, for example, ordinal values like Likert scale values doesn't really make sense. Okay, but often we want to kind of like normalize these values. For example, one of the most common normalizations is the zero mean and unit variance. Normalization where you basically have the new value that is equal to your old value minus the mean and divided by the standard deviation, or divided by the variance actually. And so basically what you want to do is you want to reduce the spread of your data as much as possible, and sometimes you also want to normalize them between 0 and 1, which sometimes makes it easier for your machine learning classifiers as well. And the reason for that is kind of like twofold. So first of all, a lot of times your machine learning algorithm or even your like summarization of your data is very dependent on the scaling and outliers. So if you just compute, for example, the mean value of this series, this guy here has a lot of weight into this calculation. And even for like height, that wouldn't make a lot of sense at all, right? So that it's just a wrong item. And so what this means basically is if you normalize this, the influence of this guy becomes smaller, okay? And another reason, for example, if you deal with height in centimeters on one, like in one feature column, but then, I don't know, maybe, what is a small, like, or anyways, like something like pupil distance or something like that, so like a value that's very small in contrast to that, right? If you compute, for example, similarities across multiple dimensions to identify, for example, clusters in your data set, the one dimension that is much larger in value range will dominate the other dimensions very hard, and even though it might not be as discriminative as the smaller dimension. So if you compute Euclidean distance over multiple dimensions, all the dimensions will be weighted the same way, but the one dimension that has a value range from like 0 to 1,000,000 is much more important to the classification, or to the distance, than a value that has a range from 0 to 1, right? And so if you have your input dimensions scaled at a very different range, like the one dimension that has the widest range will dominate the others, and you might not be able to find what you want in the data.
Why is that? Because I always thought that when we have larger values, when we are changing the weight, for example, in a simple classifier, so the sensitivity is going to be much higher, right? So,
yeah.
For example, and this is the case when we are changing the value of weights all at the same value. For example, we have a step like the mu or sigma or whatever.
Right.
But if we try to, consider the values themselves when we are changing the weight, when we want to classify, when we want to, what is it called? When we want to have to reach the optimal point.
Yeah.
So if we change the weight based on the values themselves, are we gonna face this issue again, or?
Yeah. So you will face this whenever you try to like optimize over multiple dimensions. So like in k-means you would have this if there's one or like a couple of dimensions that
Right,
are
in k-means
small,
that's
right.
the whole idea.
Right. but also in
It's
regression, for example, it's a big problem.
Mhm.
But then also, like you gain a lot more. Well, so in if you have like a neural network that has a couple of dimensions that are very large, like your weights might be very weird in that case, but and the adaptation there might change. So it's just recommended to kind of have them in a similar range across all dimensions. It just often works better. And I think also like in support vector machines you would have that problem as well. If one dimension dominates. Yeah, it's just like recommended to have. It's not that it wouldn't work at all, like but it might cause trouble. Okay. All right. So and then often like one of the things that we want to do is we want to recognize patterns and we want to aggregate data, and often like what we need to do there is, for example, summarize our data. And two possible ways, and like this is also kind of like in your project, I would like to see some statistics, and we would like to see some mean, median, quartile, standard deviation values for different dimensions, and maybe even like see, okay, in class 1, this mean is like this, like 0.2 with a variance of 0.3, and in class 2 this value is 0.8 with a variance of 0.5. So you would have statistical differences between the two classes, so this is kind of giving you an idea of like which feature will be helpful to classify the differences between the classes, and then some graphs like box plots and histograms and so on. Yeah.
Sorry, coming back to the same question. Yes. If you have a wide data range,
Yeah.
wouldn't it be easier to classify it? I mean, I get it if you're taking a mean of it, the higher value will influence the entire mean. But if you're just doing a plain classification, won't it be easier to classify if the gap between data ranges is big?
Well, not necessarily. Like even though the values might be large, the difference between like this, like in this dimension, the values might be large, but they might not be indicative of the class that you want to look for. So it might just be, I don't know, for example, what is a good example? It's very hard to come up with these with examples ad hoc. I only find examples where you're right. So for example, if you want to classify who are lawyers, or male lawyers versus male not lawyers, and you look at their height and their annual income, the annual income is a much larger range, but like, and it's probably the one that's more indicative of like separating them. Yeah, I don't, like, yeah, there are examples, but I can't really come up with one right now. I'll think of maybe something where it becomes quite clear, but yeah, just trust me in that range right now. There are, and most of the time this problem is just because we use simple distance measures or distance metrics. So for example, Euclidean distance weighs every dimension the same way. So like they're all equally important to the distance. But for example, Malinobis distance would take into account the variance of a single dimension before like taking it into account. And if you have a very low variance in that dimension doesn't count as much as if you have a wide range, a wide variance there. So it makes a lot of sense to look into different types of distance metrics. But if you take the simplest distance metrics, you're very dependent on these ranges and outliers. Again, also the difference between mean and median. Median is not that dependent on outliers, but the mean is very dependent. And so sometimes it makes sense to use a median, sometimes it makes sense to use a mean value. And yeah,
I made an experiment in my own work, and I had the sensor of accelerometer, and I had the sensor of orientation, not orientation, but angular velocity. So one of them, the value was much bigger. So when I normalized the data, the time, I'm not sure, but I just used the MATLAB TikTok stuff.
Yeah.
But when I normalized the data, so the time that the libSVM reached the result was less when it was not normalized. But I'm not sure. This happened last week.
Makes sense, yeah.
When you normalize your data, it reaches it's fast.
Okay.
I'm not sure, to be honest. Maybe my computer was running real computer.
No, I think you might be right. Yeah.
I think I'm
And then so sometimes we also need to visualize and represent information such as these temporal series, and this is just an example from kind of like the work I'm doing, where you would have this kind of like sentences, and you have these fundamental frequencies which are represented here as these dots over time, and so this is time on the x-axis, and what would be an important like measure or representation of this behavior could be, for example, the mean pitch value, right? But the mean pitch value would be somewhere here, and it wouldn't really like capture something that's going on back here, right? So sometimes it makes sense to split your data into time sequence, into bins, for example, first, second, and third, and you see in the third it goes up. Sometimes it makes sense to just calculate the derivative or the second derivative of your data to represent the data, what's happening. So first derivative will give you like a slope, what's happening to the data in across a certain time. The second derivative would give you like how many times does this slope change in my data, and so on. So there are a couple of things that just make sense to think about, and this is also why I always encourage people to like look at the data first, try to understand what's going on in the data, try to make sense of what you have and what might make sense for you to capture and to provide to the machine learning algorithm. Even though nowadays everybody's just throwing data at machine learning algorithms. And there are benefits to either one of those approaches. Okay, so just to summarize some descriptive statistics, so arithmetic average, the mean, median, basically you sort your list and you find the middle, and that's your median, and the mode is like the one sample point that has the most observations, and then just as you know, the median is less dependent on outliers back there than the mean, so just so you know, basically. Other descriptive variables, so for example, the variability of your data is captured in your variance or standard deviation, which is the square root of the variance. And oftentimes your data will be represented in like this normal distribution or Gaussian, where in the middle you have your mu, the mode of this distribution, which is the mean value, so to say, and then you kind of have data that's one standard deviation away, 2 standard deviations, and so on. And this is important for understanding like how your data looks like, but also for statistical analysis and to like compare if 2 distributions are similar or sufficiently different from each other. And we'll come back to this, and like there's a nice way to visualize this approach in a nice compact representation. And I really like to see in the projects, if you have a chance to like visualize your data in statistical analysis and like visualize what's going on in your data. This is more just for your reference, that we kind of need to know about these things. Then there are other descriptive statistics that could also be useful as features that could go into your machine learning. So we said the mean or the median value is kind of important. There's something about like the lower and the upper quartile. So this is basically the lower quartile, 25% of the data is in here. The upper one, 25% of the data is in here. And then 50% of the data is in here. And then the rest of the data is out there, okay? So that's kind of like the idea how to visualize those. And in MATLAB, for example, you can calculate any percentile. You can say, like, I want the first or the 99th percentile. And sometimes these percentiles are actually pretty cool to use. So for example, one of the things that I often do is I get my data set and then I clip off, like I cut off every data point that is in the range of like the 97th to the 100th percentile and the 0 to the 3rd percentile, because you often just like remove your outliers. Like if you assume that you have like 3% outliers, you remove those automatically, okay? So that kind of sometimes makes sense. Alright. Another interesting concept is correlation, where you have two variables and you want to understand like what their relationship is. You compute this through this measure here, which is basically value, has a value range between -1 and 1. And so we want to know what the relationship between my value sample X and sample Y is. And you compute this through this, and this shouldn't be like new to you. You should probably have seen this before, but just to like talk about this a little bit, because these values can be very important to know to understand like the relationship between what's going on and what you observe. But mainly A1 as the output of this function would be there's a perfect linear relationship between the two variables, and then you have these different grades of like, and then you have 0 relationship when they are like independent from each other, and -1 if they have a perfectly negative relationship towards each other. And the same thing, what this doesn't capture is the steepness, so it could be always like value, like could be in a different range. What is the correlation of this in the middle here? It's 0. There's no relationship between the value, because one value is always staying the same while the other one changes. Okay. And what is important here is that this relationship doesn't capture all relationships that exist, right? Because, for example, for all of these examples, the correlation is 0, even though there are clear clear relationships between the data points, right? And so, for example, just as an easy example, what will we do here to find a relationship? We could do clustering, for example. Very easy, right? And so this is kind of like just also for reference, like there are relationships that these like linear correlations do not capture. Okay? And then to conclude this, we can also talk about graphical representations. We'll have like maybe a pretty old but interesting paper that we can read on this. That's about how to visualize data, and I would like to talk a little bit about this. So for example, histograms are pretty cool. They give you a nice distribution of your data. So this would be, this is actually from a paper that I published quite a while ago, where we investigated how much time between two people that talk to each other is spent with pauses. And the interesting part is that the most observed value is actually negative. That means most of the time there is 0 pause. There's actually a negative pause. Like actually most of the time in a dialogue people overlap each other, right? And so there are many times where like people even overlap for 6 seconds, like just talk over each other. But sometimes there are also pauses that are just, and like I guess like if it's 6 seconds of pause between each other, it would be freaking long. Like it's just like weird and awkward, right? So there, it's kind of interesting, and this frequency is just a number of times we observe this value, okay? It's kind of cool visualization. So this gives you like a little bit of an insight here. Then you could like put in a mean value, okay, so you have like the mode, or you would have like the median. You can guess where the median is, and you can kind of guess where the standard deviation is, but you can't actually read it from the data, okay? Another visualization would be bar plots, where you basically have like the two things, and you have like the mean value for each of the classes in this case, in this case, in this case, but you don't see the standard deviations, you don't see the distribution of your data. So you can enhance this box plot to make it more cool, this bar plot to make it more cool, and like one way to do this would be box plots, where you now have really a compact representation of what's going on. So you have your mean or median value, you can choose whichever you want, and you have your quartiles, or a certain number of quartiles. So this, for example, could also be 1.5 standard deviations up and 1.5 standard deviations down, and then this could be like the outliers or something like that. So these are very compact representations of what's going on in your data, so these are kind of cool. I like those plots, just for your reference. Another thing that's interesting are scatter plots. Scatter plots are really great to visualize relationships between two variables, but they're really bad at like finding the mean value or the median value and stuff like that, okay? But scatter plots with regression lines, for example, are kind of cool. You can see the relationship right away, and you can evaluate like what's going on here. Let's talk a little bit more about the box plot. Basically, the box plot can be visualized as such. If you have like a perfect normal distribution, you would see the relationship like this, and the box plot basically just turns this around and visualizes it as this. Okay, so this is what these guys are representing. So you have like a really nice compact representation of your data in this kind of tiny box, and you have very compact information about what's going on. What I like to do when I see statistical differences between two observations, I like to add these brackets with stars, and the star would be like showing statistical differences. Here, for example, there are no statistical differences, and so on. So these are kind of like things I like in visualizations. Okay. And then, just for reference, there are many other ways to visualize information. So, for example, these word clouds, which are kind of cool sometimes, where you can visualize the most important, the most frequent words in your data. So I guess this one was looking for architect or architecture. Yeah, where you have design and lighting and technology comes in, but then also like some, you know, artsy mind. Need to think about the human mind and yin and yang and stuff like that.
We should,
Yeah,
but we don't.
I think yeah, environment should be larger, but anyways.
Oh, no, I think it's the right size.
But then also, there's this whole big research area of like data visualization, and kind of started with this data visualization, which I like a lot. It's very informative, and it gives. Does anybody know what this is? Yeah, so it's Napoleon's March, where the beige one is like the number of people that marched towards, what is that, Moscow, I guess?
Yeah, Moscow.
And then this is how many came back. So you can see that it's a lot less than left. So yeah, this is kind of a cool area. So if you have interesting ways to visualize your data, I encourage you to use it. It's kind of nice to look at and discuss your, or try to help you find what's going on. All right.
Architects are obsessed. There's somebody who was visualizing winds in processing, so there's a
Oh, yeah?
yeah.
There's also good visualization.
Processing. Processing, which is Java's plugin.
Oh yeah, that's a
Java
good
plugin,
visualization.
which is a lot, yeah.
It's like Java, right?
Yeah, it's Java, but takes care of Java's G class, G frame class, this nonsense. And kind of simplifies it.
Yeah. There's
So
a lot
to
of
plug in.
DJs using to visualize using stuff.
The pro they use Max on top of it or something. Yeah.
But yeah, processing it.
Processing and then apps design.
You can still
What time does the channel leave or?